Good morning, guys. Today we're going to work with modeling, doing some modeling with quadratic functions. A model is just an equation that describes a specific relationship. In this scenario, we're looking at quadratic relationships. That's groups of points that have, that's groups of points that would fit a parabola or have a parabolic shape to them. So we're going to look at a couple of different things about the relationships between the points that let us know that they're quadratic, and even be able to write the equations if we're given some points for the quadratics. So let's first look at what makes a group of points quadratic, or linear for that matter. So first off, if a relation has a constant first difference, we call it linear. Constant first difference. That means the first time I find the distance between the x's and y's, it's linear, which we know that to be true because when we do slope, it's change in y over change in x. That's that constant first difference. The first difference in the y's and the first difference of the x's have the same ratio. Well, a quadratic says if a relation has a constant second difference, then it's quadratic. So linear is the first degree, first difference is constant. Quadratic is second degree, so the second difference is constant, and that holds for all polynomials. So whatever it is, if I want to know if something has fits a fifth degree polynomial, I would check the fifth difference right there. Now, if they come out to be constant, then yes, it's going to be a perfect fit. If they come out as almost constant, you could get a quadratic that comes very close to it, and that gets into where our modeling and our predictions and our regression lines come in. But let's look at ones that are actually a perfect fit. They are either the first difference is linear or the second difference is constant, making it quadratic. So let's say we have this problem, this relation right here. So we have all these points and we want to find the differences. Well, we're going to start with the x's. So we can see that the x's from -3 to 1, we increase by 2. -1 to 1, we increase by 2. 1 to 3, we increase by 2. And 3 to 5, we increase by 2. So the x's have a constant difference, so we're good there. If the y's have a constant difference, then we would say it's linear. So let's check our y's. So the first difference, from 6 to 2, we have a -4, so we decreased by 4. From 2 to 6, we added 4. So we know right now it's not going to be linear, because while the x's had a constant first difference, or while the x's were the same distance apart, same change, the y's do not have the same change. So we know it's not going to be linear, but we go ahead and finish it figuring out what the first differences are. So from 6 to 18, we increased by 12. 18 to 38, we increased by 20. So first differences were not constant, so we know it's not linear. Second differences, which is what we're focused on because we're looking at quadratics, from -4 to +4 is an increase of 8. From 4 to 12 is an increase of 8. And from 12 to 20 is an increase of 8. So since we have a constant difference in y's, for my second difference, for evenly spaced x's, we can say that we have a quadratic function. If the same distance had occurred in the first difference, then we would have said it was a linear function. And if it didn't happen in either one, it would have to be some other degree polynomial, or maybe not even a polynomial. It could be some other type of function. But that's what we're looking at right here. Now, with the first difference, we remember that our slopes don't have to be the same number between them, but the ratio of the differences has to be the same. So we always do this double check with the x's originally to make sure that they're equally spaced. Then we get to look for that constant first or second difference. If not, we're looking at the ratio of first differences to the x's and second differences to the x's. All right, so here we have an example. Determine whether each data set could represent a linear function, quadratic function, or neither. That's just a fancy way of saying check the first difference and check the second difference. So if I check my x's first, increase by 1 from 1 to 2, 2 to 3, we increase by 1, 3 to 4, we increase by 1, and 4 to 5, we increase by 1. Now let's check the y's. -2 to -5, so we're checking our first difference, is decreased by 3. To -8, we decrease by 3, decrease by 3, decrease by 3. So since we have a constant first difference, we can see that we have a linear function. And we don't have to go any further than that. Okay, just take a quick second. I'll wait right here, and you guys check and decide, is example 2 here quadratic, linear, quadratic, or neither? Okay, hopefully you were able to come up with an answer. Let's check it out. So the x's, we can see they increased by 4, increased by 4, increased by 4, increased by 4. So we have equally spaced x's, so we're allowed to check first and second differences. So first difference, -5 to 11 is an increase of 16. 11 to 19 is an increase of 8. 19 to 23, an increase of 4. And 23 to 25, an increase of 2. So we can see that first differences are not constant for equally spaced x's, so we know it's not linear. Let's check the second difference now. From 16 to 8, decrease of 8. From 8 to 4, it's a decrease of 4. And from 4 to 2, that's a decrease of 2. So for second difference for equally spaced x's is not constant, so that tells us that we do not have a quadratic either. So this one we would say is neither linear nor quadratic. And that's it. That's all that we have to do to determine if a data set is linear or quadratic. Now, as I was saying before, the points may not match exactly, in which case it is a neither. But if they were very, very close, say that we had gotten a second difference of a -7, a second difference here of -8, and a second difference here of -7. Those are very close to being constant. So while the points don't make a quadratic, we could get an equation, a line of or a regression line for a quadratic that's close to those points. And that's something that we're going to look at as we get into example 3, those regression lines. All right, but first let's take the points and figure out what the equation is. So we have some points, we know that they're quadratic, and let's decide what the equation, what the model actually is that fits those points. Well, we have our standard form of our polynomial, of our quadratic function, is y equals ax squared plus bx plus c. Well, as you know, we would need a, b, and c to figure out what the quadratic is to be able to have our equation, because the y's and the x's, they stay. Well, that's 3 unknowns. Well, if I have 3 unknowns, then I need to come up with 3 equations to be able to find those 3 unknowns. That's a system of 3 equations. So here you can see what I do know, because I have a bunch of points, is some x's and y's. So if I need 3 equations, I need 3 sets of x's and y's. So to be able to write a quadratic function, I need 3 points. 3 points on the curve. Just like when we wanted a linear function, we needed 2 points on the curve to be able to make the equation of that line. So quadratic needs 3 points. If I had a cubic, I would need 4 points, and so on. All right, so here's our system of equations. y1, the first y is equal to a times the first x squared plus b times the first x plus c. The second y is equal to a times the second y squared plus b times the second, a times the second x squared plus b times the second x plus c. And the third y is equal to a times the third x cubed. Let's try that one more time. The third y is equal to a times the third x squared plus b times the third x plus c. So all we're going to be doing is taking our first point, that's x1, y1. Second point, that's x2, y2. Third point, that's x3, y3. We're going to put the first point into the first equation for the x's and y's. Second point into the second equation for the x's and y's. Third point into the third equation for the x's and y's. And we get something like this. So you can see y1 was 3, x1 was 2, so 3 equals a times 2 squared plus b times 2 plus c. So the x's and y's come out, and the 2 and the 3 go in. In the second equation, 3 and 13 replace the x's and y's, so it's 13 equals a times 3 squared plus b times 3 plus c. And the third point goes into the third equation. 4 goes in for the x's. 29 goes in for the y. So you'll get that equation. 29 equals a4 squared plus b4 plus c. Well, we have a system of equations, 3 variables, 3 equations, and we just solve our linear system. And we know there are a lot of algebraic techniques that we can use to solve a linear system. We're going to use a calculator technique to be able to solve this linear system. So I'm going to first write it as a matrix. First, I'm going to turn my calculator on. So I'll hit second matrix, go over to edit, and this has 3 variables, or 3 rows, because it's 3 equations, and 4 columns. Remember, I have an A column, a B column, a C column, and a constant column. And remember, put them in that order. A's, then B's, then C's, then constants. Your constants always have to get at the end. And I just type. So my A coefficient is 2 squared. My B coefficient is 2. C coefficient is 1. My constant is 3. So I'm just making my normal augmented matrix, coefficient matrix with the constant matrix augmented on there. Second row, 3 squared, 3, 1, and 13. Then the third equation, third row, 4 squared is for A, 4 is the coefficient of B, 1 is the coefficient of C, and 29. Let's go through, double check it. So 4, 9, 16. Remember, A's were first column. 2, 3, 4. B's were the second column. 1, 1, 1. C is the third column. And 3, 13, 29. So there are our 3 equations. Now we're just going to use the RREF function to solve it. So we second quit. Go back into second matrix math. Remember, go over to math column, the math tab. And you just go to RREF. That's going to put it into reduced row echelon form. Remember, this is just doing all your Gauss-Jordan elimination steps for you and jumping you straight to what should be the solution. RREF. Reduced row echelon form, or a really, really easy way to find the answer. So RREF, and then we second matrix, tell it to do it for matrix A, hit enter. I have my identity matrix on the left side, so that means the right column is my solution. So 3, negative 5, 1, and remember how to read this. This was my A column, so 1A equals 3. 1B is equal to negative 5. 1C equals 1. So if we have y equals ax squared plus bx plus c, we should get our final function, y equals 3x squared minus 5x plus 1. A was 3, B was negative 5, C was 1. So that is the equation that fits those points. If I wanted to check that, I could go into y equals and type it in. 3x squared minus 5x plus 1. And look at the table, hit second table. And you can see that at 2, x is 2, y is 3. At 3, 3 is 13. And at 4, we have 29. So those points all showed up in the points, the table for this quadratic function. All right, let's have you do one example yourself. All right, so I'll sit here, wait for a couple minutes, pause the video. This one will probably take you a couple minutes just to get it set up and plugged in. And you guys try this one out and let's see what if you can come up with the correct quadratic function for those 3 points. And I'll wait right here, guys. Okay, hopefully you were able to get a solution. Let's check and see what you got. So we know we're trying to get y equals ax squared plus bx plus c. So when we substitute into our first equation, 0 goes in for the first y, 1 goes in for the first x's. So 0, 1, 1. Second equation, negative 3 is our second y, 2 is our second x, so that goes into the second equation. And negative 10 is our second, negative 10 is our third y, and 3 is our third x. So we just plug those in. Let's go grab our calculator. and plug her in. So second matrix, edit. 3 rows, 4 columns. So 1 squared is 1. B coefficient is 1. C coefficient is 1 equals 0. Second equation, A's coefficient is 2 squared, so that's 4. B coefficient is 2. C coefficient is 1 equals -3. Third equation, A's coefficient is 9. B's coefficient is 3. C's is 1. That equals -10. Remember, constants are your far right column. A column, B column, C column. Constants are the far right column, the fourth column. Okay, we second quit. If the calculator wants to cooperate. Second matrix, math. RREF, reduced row echelon form of second matrix A. Enter, enter. Identity matrix, that tells me the far right column is my solution. So A should be -2, B should be 3, C should be 1. So we should get the quadratic function -2x squared plus 3x minus 1. So it's just a matter of taking those 3 points. Got to have 3 points to be able to write a quadratic. So we take those 3 points and just plug them in using solving that system of equations. All right, last thing. Let's use the regression features of the graphing calculator to write a quadratic model. So let's say we have this problem right here. It's a little difficult to read, but we'll make do. Table shows approximate run times for 16 millimeter films given the diameter of the film on the reel. Find a quadratic model for the runtime given the diameter. Use the model to estimate the runtime for a reel of film with a diameter of 15 inches. Yada, 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 yada. All right, they want us to write a model. Now, if we look at our model, well, how do we write a model if we're given a table and all that stuff? So, to write a quadratic model for a data set. First thing we're going to do, grab our calculator, and we're going to go into the Stat menu and select Edit. So if I have my calculator, and we'll punch some numbers here in a minute, but just showing you where some buttons are. Clear that out. It says go into the Stat menu. So over here by your directional pad is the Stat button, and you can see the first option says Edit. So hit Enter for Edit, select Edit, and you get this little screen here. It says type the values of the independent variable, which is going to be your x's, into L1. So my x, whatever would be on my x-axis will be my L1. And the values of the dependent variable, which is going to be your y's, are going to go into L2. So whatever would go on my y-axis would be my L2. So if I'm plugging it in, it's a domain value, it's independent, it's going to be our x. If I'm getting it out, if it's going to be the answer from the question, then we're going to say it's a dependent variable, and we're going to put that into L2. That's our y values. From there, I would go back to Stat, go back into the Stat menu, go over to the Calc tab. So Calc is that second tab over. And then we're going to select Quad Reg, which is choice 5. And from there, I'll kind of demonstrate what all that tells us. So let's go back to our problem. Oh, see, it's a little more clear now. And where it says find a quadratic model for the runtime given the diameter, well, which one is going to be the domain, which one's going to be our x's, and which one's going to be our y's? Very important, because I've got to know what do I put into L1, what do I put into L2. So we're going to put our x's into L1. Well, it says if we're finding the runtime if we're given the diameter. So we're going to start with the diameter, and then we're going to get the runtime from that. The runtime is a consequence of the specific diameter. So the diameter should be our L1, and the runtime should be our L2. The real length has nothing to do with this problem. That's just some extra information they decided to give you. So if we grab our calculator, we know what our steps were. Our steps were hit the Stat button on the calculator and then hit Edit. L1 is going to be our x's, our input values, 5, 7, 9.25, 10.5, 12.25, 13.75. L2 is going to be our y's, or our independent variables. Sorry, our dependent variables is what we get out. So 5.55, 11.12, 16.67, 22.22, 33.33, 44.45. I see a little repetition there. Just double check. Anytime you're keying stuff in the calculator, double check, make sure you didn't miss a button or double up a button somewhere. So X's, 5, 7, 9 1/4, 10 1/2, 12 1/4, 13 3/4. L2, 5, 5, 5, 11, 12, 16, 67, 22, 22, 33, 33, 44, 45. So we've keyed it in correct. Second step was go to Stat Calc. So hit Stat and go over to your Calc tab. And then we go select Quad Reg, which is choice 5. You can just hit 5, or you can scroll on down to the 5. Hit Enter, Enter, and I'll get this equation. Now, a couple things. Some of you with an 84 may be asking you things like X's and Y's and independence, or inputs and outputs, L1, L2. Your calculator should be set up to where you just keep hitting enter until you get down to where it says calculate, and then hit calculate. It'll spit this out. Now, all of you may not have this R squared put on there. That's a function that the calculator does to tell you how good your fit is. So if that number is really close to 1, then your points were really close to being a perfect quadratic. So we can see 0.996 is pretty good. So that means that a quadratic model is a really good fit for these points. So it's just something there, and I'll show you how to turn that on and put it on your calculator one day in class. I mean, it takes about 2 seconds to turn that on, and you have it ready to go whenever you need it. But we don't need it at the moment. We just want the equation. So where before, remember we did the system of 3 variables, 3 equations to get the A, B, and C? Well, this is one where if we had the second finite difference was not constant but close, kind of like I was talking about before, maybe you had a difference of 7, a difference of 8, and a difference of 7. So they're not exactly a quadratic, but it's close to a quadratic. Well, you could use this technique to figure out your A, B, and C. What your A, B, and C for those points should be to give you the quadratic that's closest to those points. So as you can see, we have y equals ax squared plus bx plus c. So A is 0.39. Just take it, I don't know, 4 decimal places. Don't round it too far. I don't want to do like 0.4 and 3.1 and 11.9, because the more you round it, the further off you get. Notice how your run times here are already 2 decimal places. So let's try to go, I like to go 4 decimal places, just because it's going to be more accurate for us. We should be accurate to 4 decimal places in. So what am I doing with this equation? Well, my equation is 0.3972x squared plus b. Well, b is negative. Let me fix that. Plus b, but b was a negative 3.12, I don't know, 01. 01 x. And then plus c. C we can see is 11.9375 or 9376. So here's the equation that these points created. A lot of things you could do at this point with it. I could take that equation and type it into y equals and look at its graph. I could take it and I can put the scatter plot on there. That's always an option. I could look at its table once I've keyed it in. So a lot of things we can do. What did they ask us to do? They said, find a model, which we did, and use the model to estimate the runtime of a reel of film with a diameter of 15 inches. Well, notice diameter was our x's, and runtime was our y's. So if I want to get a runtime, I need to plug in a diameter. So if I want the runtime for 15, I just take my equation that we just generated, my model, and I insert 15, and for x. I left a plus sign off here. That would have made a big difference. Alright, so, and it's both x's, because x is x. It's the same value at the same point. So instead of getting... Alright, come on, calculator. Second, insert. Alright, so instead of getting 0.3972x squared plus negative 3.1201x plus 11.9376, we're getting 0.3972 times 15 squared plus negative 3.1201 times 15 plus 11.9376. So we took the x's in the equation, replaced them with the 15, and we're going to evaluate. And yes, you could make that minus 3.1201. I was just trying to make it plus the b because that's what standard form is, plus b. You can clean that up if you feel the need, but the calculator will do it for you. So we see that the run time, if we have 15 millimeters of film, or sorry, a 15-inch diameter film, the run time is going to be about 54.5 minutes. 54.5 minutes. So remember, always put it back in context of the problem. Answer the question that's asked. So we estimated it to be about 54.5 minutes if the diameter is 15 inches long. That's really it for quadratic models. Being able to use second constant, second differences to determine if a relation is quadratic. If it is, then taking 3 of your points and turning it into an actual quadratic. And if you have something that's not perfectly quadratic, we can use the quadratic regression feature of the calculator to get the quadratic that's closest to your points. And then we can, once we have equations, we can do all kinds of things with them. Graph them, look at their tables, or actually evaluate at specific points in the function. That's it for modeling with quadratic functions, and I will see you in class tomorrow, guys.